Familiar? Yeah. All right. Okay. Everybody, welcome to Geography Department's speaker series. My name is Madhumita Datta, and I'm an assistant professor in this department, and I'm the chair, not of the department, but of the speaker series. And as you see, there is a great lineup of speakers for this academic year. We have 6 speakers coming, and we are starting the series with our marquee event, the Robinson Lecture. And before I invite our chair, Professor Matt Coleman, to tell us a little bit about Arthur Robinson, I would like to thank the staff and students who helped us put together this event and also will be doing so in the coming months. So thank you all, and thank you all for coming. Matt, over to you.
Thank you, Madhu. Hi, everybody. How are you doing? Good. Great. It seems a little odd that I talk about somebody else first, but I am going to do that because she is here to give our Arthur H. Robinson Colloquium for 2023-2024. So I'm going to just say a few words about him and where this comes from, and then pass the floor, mic or the non-mic over to Ellen. So Arthur H. Robinson was born in Montreal in 1915. He belonged to that very interesting generation of geographers that was shaped by the events leading up to World War II and World War II. He completed his Bachelor of Arts actually at Miami University in Oxford, Ohio. He then went on to earn his MA at the University of Wisconsin-Madison. And during the Second World War, he held a series of sort of intelligence posts in various units, including being the chief of the map division within the Office of Strategic Services, which some of you will know is the precursor to the CIA. And while actually at the OSS, he had a planetary vision. He built a massive 750-pound, 50-inch diameter globe, which he called the President's Globe, which was given to FDR in 1942. It's a massive thing. It's on display in the Library of Congress. And it was given to FDR as a visualization tool for the war effort. And matching globes were given to Winston Churchill and to General George C. Marshall, who's the Chief of Staff of the U.S. Army. And as he said, the globes offered the 3 leaders, quote, a view like that of an astronaut. That certainly would have helped them contemplate the immense strategic and logistical problems of a truly global conflict. Having done that, he then went to do a PhD. And he did it here. He did it in short order. He graduated in 1947, and then he started a career-length post at the University of Wisconsin-Madison. He served as the president of the American Association of Geographers, but also of the International Cartographic Association. He's best known, of course, for his eponymous map projection, which he invented in 1961. He famously quipped about his projection that, quote, I started with a kind of artistic approach. I worked with variables until it got to the point where if I changed one of them, it didn't get any better, and then I figured out the math. So that sort of post-math effort paid off handsomely. It was the official projection of the National Geographic Society and Rand McNally, and in fact, it's still the gold standard used in the CIA's World Factbook. The Arthur H. Robinson Fund was established in 1985. Part of that very generous fund supports the Arthur H. Robinson Colloquium, which he himself kicked off with a talk here in the department in 1997. A range of well-known scholars have addressed this under the Robinson banner, and today we are extremely pleased to have Dr. Tierney here as our distinguished Robinson speaker. Thank you very much, and I'll pass it on to Ellen.
There's one over here and one over here. Yeah, thank you. Yeah, this. Yeah, there's one over here. Right, Matt's got that one. There's one right here.
I'll get some more chairs.
Well, I have the pleasant task of introducing our guest, Jessica Tierney. She's a professor in the School of Geography, Development,
and Environment at the University of Arizona. I met her first years ago when she was a graduate student at Brown. That's me, doesn't it? So in 2010, she graduated with her PhD in geology from Brown University. She has all 3 degrees from Brown. She had specialties in paleoclimatology and organic chemistry. After graduating, she held a position for 2 years as a postdoc at the Lamont Nordic Earth Observatory of the Columbia University. That was 2 years. And then 3 years as a research scientist at the Woods Hole Oceanographic Institution. And then in 2015, she joined the University of Arizona as an associate professor. In 2022, just recently, she was promoted to full professor, and she was named the Thomas R. Brown Distinguished Chair in Integrative Studies. Her research group studies past climates over a spectrum of timescales using organic chemical techniques and statistical climate reconstruction approaches. She and her team are very prolific. I got tired of counting. So I'm going to give a lot of numbers. Along with her collaborators or their collaborators, because she researches very much in the same mode that we do, and that is in the team mode. So along with her collaborators, she has published 84 peer-reviewed publications and has 2 more in press. And then in 2020, I thought this was worth noting. It was all worth noting. This is special. In 2020, she was the lead author on a paper in Science called, it was entitled Past Climates and Our Future. And the same year, she published a first authored paper in Nature, and that was called Glacial Cooling and Climate Sensitivity. You know, we all struggle over climate sensitivity, knowing what that really is. So as you can see from these topics, she has very broad interests. The breadth of topics that she and her team investigate, to me, are truly amazing. Jessica is an elected fellow of the American Geophysical Union, which we all know as AGU. She won, and it is a great competition, the James B. McElwain Medal, and this was, the citation is, for significant contributions to the geophysical sciences by an outstanding early career scientist. She's been awarded a 5-year Packard Foundation Fellowship in Science and Engineering, and therefore she is now a Packard Foundation Fellow. She was recently, a few years ago, a lead author on IPCC's 6th assessment report. You worked on group 1, which is the physical basis, and I think on the water cycle chapter. Last year, she received the Alan T. Waterman Award, and if you're not familiar with it, it's very prestigious. It's given by the National Science Foundation, and the awardee gets a $1 million grant from NSF to spend over 5 years, pretty much in any way they see fit to support their research. Let me see. So to close, I want to mention that Jessica is out there, more so than I can say I am, because she has a Twitter account. I guess it's not Twitter now, but X. And if you want, it's at Leaf Wax. And after she talks, I'm sure she'll mention a little bit of her leaf wax work, so you'll know where that came from. She has a number of YouTube videos. She has podcasts, and I really recommend that you take time and look at her website. It's just replete with all kinds of exciting pieces of information. And a few things I thought was interesting were on one that had to do with cosmetics. Did you know that?
No, I didn't.
Well, I'll show you later. Somebody quoted some geochemistry thing we did.
Oh, geez.
Let's welcome Jessica.
Right, now I'm wondering, my cosmetics are using my name to sell, can you stop sharing and I'll sell whatever. Should say that I am actually not in a geography department. I'm in a geosciences department, but I am an affiliate in the Department of Geography at the University of Arizona, and I do participate in some of their colloquiums. So I am very happy to be here and visiting your geography department. One of the things I always liked about geography was, just that there's so many different disciplines under one roof, and I've really come to appreciate that, I think. Yeah, it's just really great to hear about everyone's different kinds and styles of research. I also want to say that I didn't realize that the Robinson of this lecture was the guy who did the projection. And now I'm very excited because this is my favorite projection. And so you're going to see a number of maps today in the Robinson projection. Win for everyone. Okay. All right, so I'm going to tell you a little bit about some research that we have done over the past 6 or 7 years to develop a technique called paleoclimate data assimilation. And this is sort of something that we've done in order to create a better view, both spatially and temporally, of what ancient climates and climate change look like. So I realize, again, everyone here is coming from a different direction and works on different things. So I'll tell you a little bit about kind of what I do more generally and sort of what I'm motivated by as a setup for some of the research I'm going to talk about. So I'm a paleoclimatologist, and I know there's a few of me in your department as well. But for those of you who don't think about this very often, I want to talk a little bit about what I'm doing and why I'm doing it. So paleoclimate, as you can see from the name, is about studying ancient climate change. And of course, when we go back beyond the instrumental record, we don't have thermometers anymore. We actually have these kinds of things, these natural archives of climate change, which accumulate in layers or rings and preserve chemical and physical and biological signatures of past climate indirectly. And our charge as paleoclimatologists is to go into these archives and then pull out information about ancient climate change. You can probably imagine that there's a couple of steps in doing that from these kinds of things. So why do we study paleoclimate? So there's a lot of reasons, right? I mean, it's cool, and I'll show you some cool stuff that I hope you think is cool as well. But there is actually a really pressing reason why we're studying paleoclimate, which is that we are currently doing a massive experiment with the climate system on planet Earth by warming it up. So what you're looking here is the change in global temperature since the late 1800s from the NASA GISS product. And in particular, what you can see is that since the 1960s, there's been this pretty much regular trend upwards. So zigging and zagging year to year, but really that strong trend from the 60s, that is us. That is all human caused. So the year-to-year changes are things like El Nino and volcanic eruptions, but that trend is entirely us. So we have managed to warm the planet about 1.2 degrees Celsius above pre-industrial so far by burning fossil fuels and putting them into the atmosphere, CO2 and methane, which are greenhouse gases. Now, that doesn't seem like a very big number, 1 degree Celsius, but I think we can appreciate that it's really getting real out there. And I remember kind of feeling like this right when the IPCC report came out in 2021. As an author, even though I've been working on that report for 3 years, I didn't really feel the gravity of what it meant, I think, until the summer of 2021, when we had these series of extreme climate events that actually were like, whoa. And the first one that really hit me was actually the heat wave in the Pacific Northwest. This is an image from Portland, and Portland, Oregon is a place where they don't have much air conditioning and traditionally don't need it. And then all of a sudden it's 110 out, so people have to go to cooling centers. And I think we all heard about Light in Canada and the heat wave there, and then the whole village set on fire. And it turns out that probability of that heat wave happening in a pre-industrial climate is almost zero, almost impossible. But now it's not impossible, because we are now playing with loaded dice, right? We're playing with a warmer climate where it is way possible to have these extreme heat waves happen. And we saw it happen. And then other stuff for me in the West, we worry a lot about drought and fire. And I'm a Californian, and my state is always on fire these days. And it's actually incredible. There's been a huge uptick in California wildfires, even in the last few years. And it has been linked to anthropogenic human-caused climate change, because climate change is making summers drier. They're making summers drier in the mountains, especially, and that means it's more likely to ignite. So there are other factors involved, like forest management and things like that, but the probability of these mega fires has gone up because it's drier in the Sierra Nevada. So again, we're starting to see these connections between extreme events and climate change. And so we all want to know, like, what's going to happen and what we should expect, right? And that's part of the goal of the IPCC work that I did do as an author, is trying to figure that out. But this is actually where paleoclimate comes into the picture and can play a really, really important role. Because the fact of the matter is, if you try and understand climate change by just observing the last few decades, it's like trying to understand the rules of a game by just watching a few plays. So I know you guys are big into football here. Now, you obviously know the game really well, but let's pretend for a second that you didn't, and you saw like one down or something, and you would be really confused, right? Like, there's a lot of rules out there, right? And you don't know what they are until you've watched enough games to figure it out, right? Because it's kind of opaque. So similarly, the climate system is the same way. We don't really know its full range of behavior by just looking at the historical record, which is incredibly short and is incurred entirely under a pre-industrial climate plus a little bit of warming. So we don't know the full range of what the planet can do by just looking at human history. And that's why we need paleoclimate. That's why we need to go back into the deep past to understand how the Earth system changes when it's forced by really large changes in energy balance that can make the planet warm or cold. And paleoclimate is also about context. And I think you all have probably familiar with the work of Wani here in ice cores. Ice cores have given us a lot, but I just want to show you one of the more famous contexts that ice cores have given is that of greenhouse gases, right? So one of the cool things about ice cores is that when the ice forms, they trap air and bubbles, and then you can melt that ice and get those bubbles out, and you can actually directly measure ancient greenhouse gas concentrations going back almost 1 million years. And I think it's this context that shows us how different the CO2 is now, right? So the CO2 at almost 415 parts per million is nothing like what the planet has seen for almost 1 million years, right? It's way outside the range of natural variability. I know many of you have seen a version of this plot before, but this is the kind of context and relief that paleoclimate information can give, and only paleoclimate information can give, to put what humans have done into context. But it can do a lot more than that too, and I'll talk about a couple other examples of how we're connecting past climate to the future in this talk. But that's just sort of to give you some motivation for what I do most generally. Now, what I do on a day-to-day basis varies, but it usually involves being in this room or being in front of my computer. This is my laboratory at the University of Arizona. And what we do is we actually are organic geochemists. So day to day, we're doing organic chemistry, and that's our trick. That's what we apply to those natural archives of climate change to get paleoclimate information out. And I'm not going to talk about how we do that today because I don't have time, but I'm happy to chat with people afterwards about that. But just to say that I come at this originally as someone who generates data, as generating records of past climate. dot by dot, measurement by measurement, year over year. And over the years, we have assembled a number of records of past climate change over an order of magnitude different timescales. So we have done climate reconstruction in the last 2,000 years. We have done climate reconstruction almost 100 million years ago, and everything in between using our geochemical techniques. But you can see that we have these dots on the map where people in my lab have generated data. And, you know, they're not evenly distributed over the planet. We're very interested in the tropics. We've done a lot in Western North America. After all, we are here in Tucson. And I'm proud of all the work we've done, but you know, there's still only these dots on the map, right? And wouldn't it be nice if we could travel back in time and see what the whole planet looked like at that time? What did the whole field of temperature look like? What did the whole field of precipitation look like across planet Earth? Can we go beyond these dots into maps? And that's what has motivated the work that I'll talk to you about today, which is trying to answer this question: how do we learn about the spatial patterns of change and the climate dynamics of ancient climates? And the answer is we need to do a little bit more than just generating a record in one place and one time. We need that data, but we need to synthesize it together with data from other lab groups and different types of measurements, and also climate model simulations. And so to put those pieces all together, what we've done is we started with something that does give us a spatial point of view of the past, which is paleoclimate model simulations. So here what we're doing is we're taking the same climate models that we used for the IPCC, same Earth system models, and we ask them to simulate ancient climates, whether it be 1,000 years ago or 1,000,000 years ago or whatever we want. These are computer simulations. We can ask them to simulate whatever we want, right? So we can do that, and that is a potential view into a past climate, although it's what the computer says might have happened, and it wasn't there, right? So it's not quite reality, whereas all those measurements I was showing you are, right? But this is a good place to start. As you can see, we're in the Robinson projection. We'll continue that way. Okay, so what we're going to do is we're using this technique, data assimilation, to blend the model simulations that I just showed you with those geological observations of past climate. So what is this technique? This is actually a technique used in weather forecasting every single day. When you read your weather forecast, what you're looking at is the weather folks are running a model, a weather model, which is like a climate model, but higher resolution. And then they are assimilating, adding to their model measurements of temperature and humidity and wind speed that they've actually taken from the atmosphere. And they add that into their model, and then they run it again, right? And then they get a better and more precise forecast. So another way you might have seen this is in hurricane forecasts. You have the cone of uncertainty, and then the cone gets smaller and smaller, and they're starting to assimilate information, and they can create a more and more precise forecast. So what happens, this is sort of a nice diagram to think about it, is if you run a climate model without data assimilation, it'll give you some sort of evolution of climate. This is an example with the ocean. Let's say it's an ocean model, ocean through time. And then you want to add in these observations that you actually have of ocean temperature, let's say. And what you do in data assimilation is you nudge the model towards those observations. Note, though, that the green line doesn't intersect them. You don't nudge them all the way because the observations are a little bit uncertain as of themselves. So you want to account for that uncertainty in this addition. So we're adding together these two kinds of pieces of information. Okay, so this has been done, like I said, for weather forecasting, but how do we do this for ancient past climates? We have a little bit of a different set of ingredients and a different approach than you would in the weather application. So I already introduced our paleoclimate model simulations, which give us an idea of what, let's say sea surface temperatures looked like 3 million years ago. That's literally what this model simulation is. And then we have some, what I'm calling here proxy data. We use this word as a stand-in, right? These are proxies for sea surface temperatures, or stand-in for sea surface temperatures. So these are geological data that are sensitive to sea surface temperature. And in this example, for 3 million years ago, this is the network that we have, and this is what they say the temperature change was like, but only at certain points, right? And they're never evenly distributed because it turns out there isn't ocean sediment everywhere you like, and you can only go where there is one, and so you never get like an even sampling. Right? So we're going to combine these two things together. So the math of this is for anybody who knows data assimilation, is the ensemble Kalman filter method. And we're doing this combination offline, which just means that we actually run the model simulations all ahead of time and create a big menu or ensemble of possible states. And then we add in the proxy data, but we don't rerun the model. So unlike the weather forecasters who are rerunning after adding the data in, we haven't done that yet. And that's mostly for computational reasons, but we are looking into trying that out soon. Okay, so we have the model, we have our geological proxy data. We're going to call the model the prior state. So it's going to be X1 in this equation. And that's just all the possible climate states that could have been according to our computer simulation. And we're going to start with that. And then we have the observations, or the so-called proxy data. And these are in geochemical units. They're not in units of temperature yet, actually. So this is one of those geochemical indicators of temperature that has a funky name, Tex86, but in any case, it's not, it comes in this little geochemical unit that you measure in the lab. We're going to call that observation or set of observations Y. And then what we're going to do is we're going to take the ensemble of model simulations and forward model or simulate what the models think that observation value should be at the same location as where it is. And that's what we call YE, or the estimate of Y. So we've got what the model thinks the geochemical measurement should be, and what it actually is that we measured in the lab. So Y minus YE, that difference is the new information that we're adding to our prior state, which is called the innovation. So if the model was perfect, right, this would be 0, and then you don't update because it's perfect. So it's great. But usually that difference is not 0, right? That is added to the prior state with a weight called the Kalman gain. More about that in a second. And then you have a posterior state. And the math is actually that simple. It's in linear algebra. Of course, it's more complex to set up in computer code, and that's where it took us a while to get it working. But yeah, it's really quite a simple addition with a weight of new information that's happening. So what is the weight that we add the new information with? It's called the Kalman gain. And the numerator, so to speak, of the Kalman gain is simply the covariance between the prior state and the estimate of the proxy. And that just represents the relationship between where the proxy is and the rest of the model field. So if that geological observation or proxy observation is in the tropical Pacific, it may be related to a lot of other places through the El Nino Southern Oscillation, for example. And that information then spreads spatially away from where that proxy is. So this essentially spreads the information out beyond just the location of where observation is, but elsewhere in the climate field. And then the denominator are the error terms. So this is the spread in our model ensemble, and this is the uncertainty in the proxies themselves. So as being in the denominator, if the geological proxy we have is a bit uncertain or more uncertain, then the denominator gets bigger and the weight gets smaller, and it's downweighted in the update. So this is how we take into account the fact that our geological data is not perfect. So we want to account for that in this update equation. A little more about that numerator just to visualize what I'm talking about. So covariance is really just correlation, very similar. And, for example, if we had a geological proxy record of temperature in the city of Seattle, this would be the correlation between temperature through time in Seattle with everywhere else on the planet. And you can see that if you had information at this point, the strong red gives you parts that are positively correlated. So you would actually get information about temperature all over Canada because they're so closely related to each other. And conversely, there's a negative correlation with the North Pacific. So if you had temperature record in Seattle, you could also say something about this here. And you can see these colors become weaker the farther away you go because the relationship in temperature is somewhat localized to this region. But this is this idea of spreading the information across based on the correlation with the rest of the climate field. All right. Okay, and the other advantage of DA, the data assimilation, or DA for short, is that we can put anything we want in this prior state and update it. So it doesn't just have to be sea surface temperature. If we're using geological indicators of sea surface temperature, we need it in there, but we can also update closely related variables like surface air temperature, which is related to sea surface temperature, or maybe even precip or evaporation or isotopes or anything else. And those all get updated through this edition of the innovation. Okay. All right. So if that was a little too technical, I apologize, but I wanted to get through it. Now we can look at some fun results. So most paleo DA, this idea of combining models and proxies together has been focused on recent climate change, in particular the last 2,000 years. So what you're looking at here is a reconstruction of global mean temperature from the last millennium reanalysis, which is a data assimilation product spanning back on this time scale. And it has an assimilation every single year. So it's very high resolution. But when we started doing this work, we really wanted to immediately go back to farther back in time, to deep time, if you will, to big climate changes and see what we could do with this method. So this is a figure from the review paper that Ellen mentioned that we published in Science. It's trying to provide some perspective on how past climates can kind of compare to some of our future climate scenarios. These are sort of future possible scenarios on the right. And then these are 4 past climates on the top that correspond to these points in time. This is global mean temperature and carbon dioxide reconstruction. So the past climates give us a range of anything from like super crazy hot, right, to pretty chilly more recently, the last glacial maximum or the LGM, to some things that are in between. And these different climates sort of somewhat bracket some of our possible futures. So I'm going to start by talking about our results from the cold climate, the last glacial maximum, which is not a direct analog for where we're headed. We're headed to a warm climate. Nonetheless, as we'll see, this climate can provide some important constraints on metrics of climate change that we care about, even though it's a cold climate. So why focus on this time period? Well, this is one of the best studied times in paleoclimatology. For us, it's not too long ago. It's 21,000 years ago. This is the last ice age. So you're thinking mammoths, saber-toothed tigers, all that fun stuff. Okay, and you can see that the planet looked similar to today, except we have now giant ice sheet over North America, the Laurentide ice sheet. We have Eurasian ice sheet over here. Because of these huge ice sheets in the Northern Hemisphere, which are not there today, the sea level dropped down. We locked up all that water on land, dropped down 120 meters, which exposed some of the tropical shells and also exposed the Bering Strait up here. So you can see that. So we know from glacial information, where the edges of these ice sheets were. We know that the sea level changed pretty well. And thanks to the ice cores, we also know precisely what the greenhouse gas concentrations were for this time period. So we know a lot about it. And we also have a lot of paleoclimate data from this time period. So it's been really well studied. So this is the underlying data set that we used in this data assimilation of the last glacial maximum, or LGM for short. And these are 4 different geochemical indicators for sea surface temperature. So I'm not going to describe how all of them work because that would take a little bit of time, but there are 4 different ways that we can estimate sea surface temperature, and they all come in different units. And you can see that there's almost 1,000 data points in the last glacial maximum, which is great. But also notice that they're not evenly distributed, right? That's a challenge that we have, that in fact, you just won't find sediment out in the middle of the ocean that dates to the last glacial maximum because it doesn't accumulate very fast out there. You have to be closer to the shore. Hence, this is one of the challenges of the data set, is that it's never going to be evenly distributed. Now, for our model simulations, or our model prior starting point, we used these simulations done by my colleague Zheng Zhu, who works at NCAR in the Paleoclimate Working Group. And we had a set of simulations done where we asked the model to tell us what it thought the last glacial maximum was. And I'm just showing you some of those versions here of sea surface temperature and also the O18 of seawater, which is related to salinity and actually needed for some of our proxy data. So we had these wonderful simulations as a starting point, and we're going to combine them together using that method that I was stepped through before. And this is that hybrid or combined result that we got out of that data assimilation. So by combining the model with the data, we then get this full field view of how temperature has changed relative to pre-industrial. So this is a difference map. I could also plot like just the plain temperature, but the difference map is kind of cool because it shows you relative, to pre-industrial, not to today, would be a little bit warmer. This is how the world was like in the last ice age. So obviously it's all blue, everywhere was colder, but some places were colder than others, right? So we see deep cooling around the Southern Ocean, but also all over North America and sort of concentrated in Western Europe, maybe less cooling in certain areas of the tropics. If we take the whole global average of the change in temperature during the last ice age, it's 6 degrees Celsius cooler. And that is kind of a satisfying result, because if you try and estimate the global cooling just from those data points alone, because they don't sample the surface of the planet evenly, it's actually hard to get a global average. So this is another advantage of this technique, is that we actually do have like a global field. We can calculate that number. And that number, it agrees with a number of studies that have been trying to estimate how cool the last ice age was before. But it doesn't agree with a set of studies that would suggest less cooling of 3 to 4 C. It's more in agreement with these guys. And in particular, a lot of these, especially this one, were done with completely independent methods. So it's always nice to see that you're kind of converging with other research groups. But this sort of updated our estimate of how cold the last ice age was. So for a long time, this was kind of the canon, and we're sort of moving it down to this -6 number with our data assimilation. So why is it important to know how cold the last ice age was? Well, if you might be a researcher who works in quaternary science and might be directly interested in that, but even if you're not, this number can be used to estimate the metric of climate sensitivity. So Ellen mentioned this briefly in her introduction, but I just want to talk about this metric a little bit more for those of you who are not climate scientists and why it's so important. So this metric, climate sensitivity, is the global temperature response of planet Earth to a doubling of CO2 concentrations. And it's a way that climate scientists estimate how sensitive is the planet to CO2, carbon dioxide, right? We kind of want to know that, right? We want to know what that is, but we don't know what that is. Hence the probability distribution. This is a hypothetical one. You often see this metric in sort of plotted something like this, in numbers typically of 2 to 5 or something like that. So 2 would be that if you doubled CO2 in the atmosphere, the planet would warm by 2 degrees. 5, right? If you doubled CO2, the planet would warm by 5 degrees, right? So, why is this so important? It basically determines what the end of century climate change will be, and also determines the impacts and the extreme events and everything else. All those get worse if climate sensitivity is high, right? And like I said, we don't actually know that number exactly. Okay. So here's an example. These are 2 model projections of global temperature change under a high emission scenario from the same modeling center, a French modeling center. The blue one has a lower climate sensitivity model, and the orange one is high, and you can see that the difference by end of the century is 4 versus 6C. So which one is right? Well, it would be nice if we could know. The models, they're not tuned to have a climate sensitivity of any particular number that actually emerges from the physics in the model. So climate models really vary. Some of them are very low. And low, we say 2, between 2 and 3. Some of them are over 5. So, oh gosh, right? This is a problem that we faced in writing the IPCC reports. How do you do projections when you have this kind of spread? Okay, so that number from the LGM helped us to estimate climate sensitivity for a cold climate. So we could calculate that number. What is the temperature response to a lowering of CO2 during the last ice age? So we're going the other way around, and turn that into a climate sensitivity number. And this is the range that we get from our study. I'm comparing it here to a couple of different generations of climate sensitivity estimates. So we go back to the left. This is the estimate from the last IPCC report, which came out in 2013. And it's very broad, right? The box is broad, but the whiskers on the box also go from 1 to 6, which is a huge range, huge range. So these are the models that were used for the IPCC AR5. And you can see that they're a little bit more constrained. A lot of this big range actually did come from paleoclimate, including having a pretty poor idea of how cold the last glacial maximum was. So fast forward to 2021, when we're coming out with the last IPCC report, these are what the models do by themselves for this last round, the CMIP6 round, which is the one that contributed to the 2021 report. And you can see that they're actually running hotter than the old generation, more like from 3 to almost 6. And then here we come in with our paleoclimate estimate. So what the LGM estimate does is it more or less lines up with the lower level of the recent generation of models, but it does not include those really, really high sensitive models, the ones that are over 5. And so in the 2021 report, we were able to fold in the paleoclimate evidence together with the models to create a much more tight estimate of climate sensitivity, with the whiskers now going from 2 to 5. And so with this information, we now know that the models that are over 5 are too sensitive, and we shouldn't trust their projections out to the end of the century. That would be too extreme. So that's just that's an example of how paleoclimate can constrain a metric that's quite relevant for future climate model prediction. And it's good news, right? We can exclude out the high sensitivity runs. Okay, so that was our first example of applying, the data assimilation applying the data assimilation to a past climate, right, outside of the last millennium. So we were pretty excited about that result. But the logical next step was to do sort of a time continuous reconstruction from the last glacial maximum to the late Holocene. And this is the work of my former postdoc, Matt Osmond, who is now a lecturer at the University of Cambridge. Now for this is the data that we collected for this last glacial maximum reanalysis, which now is going to span from 24,000 years ago all the way up to around 2,000 years ago is when we ended the reanalysis. And it's interesting to look at the data distribution here. It's quite skewed to the Northern Hemisphere. And this is a problem that we often deal with when we're working with paleoclimate data, and it's sort of the, colonial impact of the paleoclimate data, if you will, and the sort of really big lack of data that we have in the Southern Hemisphere. It's constantly been a problem and really even comes into there. So this becomes an issue in terms of, we're kind of stuck with it, right? But it is sort of a call of action to say, hey, we definitely need more past climate records in the Southern Hemisphere, because we would trust our reconstruction less down there just because we have less information. So the model priors that we're starting with, again, we're using the same model, and this is again the work of my colleague Zheng Zhu. And now we are simulating climate all the way from the last glacial maximum, stepping up in time through the deglaciation, the time when those big ice sheets melt away, and then all the way up into the Holocene, the last 10,000 years. And so we have all sorts of different experiments that we did to test sort of different possibilities of climate states. And that's, again, our starting point before we assimilate all the geological information. Okay, and this is the product that we get by combining those two pieces of information. And in fact, it's resolved at 200-year time steps. The reason for that time step is, again, we're using ocean sediment data, and that's about the resolution that they have. So they don't have annual layers like ice cores or tree rings out there. They're a little bit more granular than that. So we just sort of have to work with kind of centennial level information. And so this is actually a global mean temperature average of the evolution of Earth's temperature for the last, say, kind of 23,000 years or so. And so the last glacial maximum is here. And what's interesting to us is that, there's actually quite a bit of structure, within what we consider the last ice age, that it's not completely uniform. There's a trend in global temperatures. It starts at around -6, which is what we got from our first study, but actually intensifies all the way up to 18,000 years ago. where we almost drop down to, well, I guess it's -7 degrees Celsius, but -8 in the fringe. And then the planet starts to warm up. And there's a little bit of a pause right here that corresponds with the Northern Hemisphere Younger Dryas event. And then we keep going. And then in the Holocene, it's relatively uneventful until we get to humans. And then you can see that, yeah, the temperatures that we have today have never been exceeded in the last 23,000 years or so. So that was one result of the study. And each of these slices in time comes with a Robinson map, if you will, or actually you can plot it in any projection if you like, but a map that you can plot up of temperature. So here again, those are difference maps relative to 2,000 years ago, which is the last slice that we do, because there are other higher resolution reconstructions of the last 2,000 years, which is, for example, this is that last millennium reanalysis once again. Okay, so this is pretty cool. This is sort of extending Earth's temperature history back beyond the last 2,000 years to the 21,000 years ago in a time continuous way, again, made possible by combining these two pieces of information that we have about past climates. All right, so this is stuff that we have done, and now I want to show you some stuff that isn't published yet, which is always exciting. We're continuing to do this. Everything I showed you, right, is going back to a cold climate, but we want to look at the warm climates, right? Because after all, that's where we're going. So I'm going to show you some results from the warm Pliocene, which is a time period 3 million years ago, which we have estimates of carbon dioxide concentrations that are actually now perhaps a little bit lower than where we are today, but somewhere around 400 parts per million or maybe high 300s. We don't know sea level rise super precisely, but we know it's about 20 meters. We also know that we probably lost most of the Greenland ice sheet 3 million years ago, and most of the Western Antarctic ice sheet, hence the 20 meters of sea level rise. So this is at a CO2 level that's similar to today, right? We've lost a lot of the ice sheets 3 million years ago. So this is a time period of big interest for obvious reasons. The CO2 level is similar. We've seen a lot of warming in the Pliocene, so can that tell us something about what we're going to expect like in the near term, right? So you can see this is a climate model simulation of the Pliocene by my colleague Ron Fang at UConn, and it just shows you, this sort of classic pattern where you tend to see much more warming. This is relative to pre-industrial in the high latitudes, especially in those places that have lost their ice, than you do in the tropics. But again, we would like to create this sort of hybrid product, data model product of this warm climate. So one of the features of the Pliocene, beyond the fact that it's a little bit warmer than today, is this other sort of funny thing, which has been called the permanent El Nino. Okay, so this is something that was first raised in 2005, I think. And so almost 20 years now ago. And it comes from, the actual data observation that this group led by Michael Wara, they measured proxies for sea surface temperature in 2 places across the tropical Pacific, one in the east and near the Galapagos, and one in the west, kind of offshore from Indonesia. So the western one is in red, and the eastern one is in blue. There's actually 2 different kinds of chemical proxies here, so blue and green, if you will. So 0 today is here, and then 5 million years ago is here. And what you see is that from 5 to 3 million years ago, the temperatures in the west and the east were almost the same. Whereas today, there's a huge difference between the west and the east. The eastern tropical Pacific, near Galapagos, is actually pretty cold. There's lots of cold water that's upwelling there. So it's about 6 degrees cooler than the Western Pacific. And that's because the trade winds are blowing and they're driving upwelling, and so that should be that way. So how come this suddenly collapses 3 to 5 million years ago? And so they gave it a name. They called it like the permanent El Nino, because during an El Nino event, the Eastern Pacific warms up and sort of relaxes that thermal gradient between the east and the west. And so they kind of used it as an analogy as to what was happening. But physically, this is very difficult to explain, as it turns out. If the trade winds are always blowing from east to west, then could you ever have a situation or the east and west for the same temperature? And it's hard to explain with physical oceanography, as it turns out. So real head scratcher. Okay, so we published a paper in 2019 where we argued that it wasn't quite a permanent El Nino. You know, maybe we should call it something else, and maybe that's too extreme. So the short story from this paper is that we went back and we reanalyzed, this is in data world only, we reanalyzed all of the sea surface temperature indicators in the Western Pacific and in the Eastern Pacific and created this composite curve. And this is the change in SST in that zonal gradient relative to pre-industrial. That original paper I just showed you had a reduction of about 4C between the East and West, really, really, really large. There's another paper that estimated something close to 3. This change would be equivalent to what we would see during a strong El Nino event. So I'll call that the boundary of permanent El Nino. But it turns out that our orange line was nowhere near these older estimates. And so we argued that, yes, the Eastern Pacific was warmer than the West, and there was a relaxation of that gradient, but it wasn't a permanent El Nino. And this is what the model simulations were showing for this 3 million year old period, this mid-Pliocene warm period. And they're actually a little bit weaker than the data. And some of them do something completely different, but they're in the error. So we went and said, you know, you can explain this with the greenhouse gas forcing, and you don't need something weird happening to the Pacific Ocean to happen. But anyway, you know, we're still debating, right? Like, how extreme was this change in the gradient? Was there a permanent El Nino or not? On and on. So one of the motivations for doing the Pliocene data assimilation is to look at that problem, as well as other problems of how regional warmth varied during the Pliocene. Okay, so we took, again, we're starting with climate model simulations. So this is just the mean value of the change in SST and surface air temperature during the Pliocene. And this just shows you the range of temperature change that's in these different model simulations for the warm Pliocene relative to pre-industrial. We always use pre-industrial as our baseline, in case you haven't noticed. So all these different model types, they simulate anywhere from like a little bit less than 2 up to 5 degrees warming for this warm period, which is a pretty big range. And then these runs over here are pretty wild. So these are what I'm calling perturbed cloud simulations. These have altered the planetary cloud albedo or the low cloud cover in certain places on the planet. And clouds actually have a huge impact on Earth's energy balance because they do 2 things. They both reflect sunlight, but they also trap heat. And so depending on the kind of cloud and where it is, you can like radically change how the planet behaves. So these are almost like idealized simulations, just messing around. One of the ideas about the permanent El Nino is that there was a dramatic change in cloud cover. So that's where this kind of comes from. And those simulations are the work of Natalie Burles at George Mason. So when we look at the tropical Pacific gradient, the change in the tropical Pacific gradient, this family of models all simulate more or less a relaxation or a reduction of the gradient, but the cloud models are all over the place. Some of them are really extreme, basically permanent El Nino simulations. So we have this huge range of possible climate states, and we're gonna say, okay, what do the data think actually happened for this time period? So here are our data that we collected. So we always, when we do these data assimilation experiments, we always do a pre-industrial one to sort of match up with our ancient ones to compare. You know, lest our proxy network impart some kind of bias, we also want to have a pre-industrial slice to kind of assess that. So that's why we always have sort of a pre-industrial slice. And then we collected data for that 3 million year period that I've been talking about, and another one even farther back in time at around 5 million years ago. And these are what the data say the change in sea surface temperature looked like, right? And we're going to combine that with the models. So here's some preliminary results that we have. So again, this isn't published yet, so we're just working on this right now. Basically, so this is just showing you the sort of full field picture of what the hybrid product looks like. Again, warming relative to pre-industrial for the full model ensemble. And then I did one just with the funky cloud runs. just to see what would happen if we only use those. And, you know, they look similar to each other, which is actually good news, that the data do kind of push things around pretty strongly. And if you look at global mean temperature change, it's not too different either. It's around 4 degrees warmer during the Pliocene relative to pre-industrial. And this is showing you the change in the Pacific gradient. So you can see how there's like that warming over here, and then maybe a little bit less over here. So there is a little bit more warming in the east and the west, so that the zonal gradient, the west-east difference, has gone down by 0.5 degree, and it's a little bit more extreme over here. And this is just what the model prior says by itself, no data assimilated, just for reference. So there is a reduction here, but it's really modest, which is actually a little bit surprising. Let me go back to 4.75 MA. This is the earlier Pliocene. It's a little bit warmer. Probably CO2 is a little bit higher. You know, we're not totally sure. It's hard to estimate CO2 this far back. And now we see stronger patterns of climate change. We see a global mean temperature change of about 4.5 degrees. And now we see more intensified warming in the upwelling area of the Eastern Pacific, collapse of the zonal gradient closer to -2C in this particular time period. But it's not -4 or -5 or a big number like that. So if we go back and kind of compare it to the previous study that we did, what we found is if we look at that 3 million year time period that I reconstructed with data alone before, we actually see pretty good agreement with the data only estimate, which might be expected because we assimilated the data, but still the model didn't, you know, the data didn't select for a deeper reduction in the gradient. So that seems like a good estimate of about -1. The early Pliocene is a little more extreme. It would be off this timescale, but we still don't cross that boundary ever of the permanent El Nino condition. And so, you know, yeah, no, trash emojis, let's not use that term anymore. So it makes people really mad, the permanent El Nino term, because it's like El Nino is an oscillation, but it's not supposed to be a permanent state. So some people have, maybe including myself, strong feelings about the term. But anyway, so it's cool to see what the PLIODA takes to the table. Okay, so then for the final thing I just want to show you is we focus a lot on this time period that's in this plot, which is the last 100 million years, which I'm sure to a lot of you seems like a really long period of time. But in geological time, it's not that long, right? I mean, geological time is vast, right? It's 4 billion years, and we're not going to go back that far, but we have had this really fun and ambitious project for the last 3 years to use the data assimilation technique to reconstruct the temperature of the Phanerozoic. The Phanerozoic means the last, well, basically since the Cambrian explosion. So life that you can kind of know and understand. There was multicellular life before then, but anyway, you know. So the Phanerozoic, we don't get quite back to the Cambrian just because we run out of data, but our reconstruction goes back to the Ordovician, 485 million years of temperature history. You may be wondering why we are doing this. I can tell you why. This is actually a collaboration with the Smithsonian Museum of Natural History in Washington, D.C. They renovated their fossil hall recently, a few years ago. It's very beautiful. It has big dinosaurs, and but it also has an Earth history theme. And they wanted in a panel the temperature history of planet Earth as far back as you could go, right? And so they convened a bunch of us in 2018 in DC to talk about how we might possibly actually come up with that graph, because it didn't exist. We said, wow, that's really hard. Like, how we don't actually really know the temperature history going back that far in time and how we do that. And so there is a plot on the Smithsonian wall right now that is up there, but before about 100 million years ago, it's basically made up. Like literally a guy like drew a squiggly line on a whiteboard. I'm not kidding. It's pretty embarrassing. And actually, if you've ever been there and seen it, you'll notice it looks kind of cartoon. Yeah. So it's not scientific, right? So, but we said, you know what? I think we can do it. We can do it with data assimilation. And fortunately, we have some colleagues over in the UK at the University of Bristol who, for reasons I'm not entirely sure why, but I guess just because it was cool, took their climate model and simulated every 5 million years through the Phanerozoic systematically with their climate model, with multiple values of carbon dioxide, with slightly different other assumptions, just because, you know, whatever, they were interested. And I'm like, oh my gosh, that's great. That's a model prior we can use, right? Well, then we face the problem of the data. And this took about 2 years to collect the data collection that spans as far back in time, which was everywhere. I should say there isn't like a single place on the internet where you can get all this stuff. Every time we do one of these things, we have to go out and download papers and download Excel sheets and then format every single thing by hand. And then we check every single record to make sure that there isn't sort of crazy, you know, missing values. It's an enormous amount of work. And this time we employed the whole community to help us out. And we published the data compilation in 2022 as FAN-SST or Phanerozoic SST. So now everyone can use it and no one has to go through that pain ever again, maybe. But okay, so that was a huge effort. It's easier to get the model stuff than the data stuff, right? Okay, so we are going to use our technique to do this. And this is what we have put together so far. So, you know, it's pretty amazing to see Earth's temperature for the last 485 million years. You know, I think it should make you smile because no one's ever done that before. So this is really cool, right? So we just submitted this paper and the little fishies are the mass extinctions. So, which some of our co-authors did not like because they pointed out that there weren't fish. Anyway, but I was like, what? We can't put a skull and crossbones because that's so human centric. And so we had all this, you know, which dead emoji do you want to use? And the fish one. Yeah, so we know about where the mass extinctions are, right? So we can see the Ordovician extinction is actually unique because it's associated with a glaciation that's known. And our reconstruction shows a sharp drop in temperature there. This is independent. This is just like a geological evidence for big ice sheets that's plotted on the top. And then most of the extinctions, the mass extinctions, are associated with warming events, and probably the most famous is the Permian Triassic, when 90% of everything goes extinct, and that's associated with a very, very strong global warming at the time. So we do see that. This one, the dinosaurs, you know, there wasn't much global temperature change on a long time scale. That's because it's from the asteroid slamming into planet Earth. And there was probably a lot of extreme climate changes that happened very fast, but it wasn't related to volcanism per se. Yeah, so it's kind of cool to see, you know, that we do pick up some climate changes of the mass extinction, but we also can learn from this quite a number of things about the range of Earth's temperature response for the first time over very, very long geological timescales. So a couple ways to sort of visualize that. On top is a sort of stripey diagram of the climate state. So we basically took the quantiles of the global mean surface temperature and just kind of colored them by different states. So from hot house, warm house, transitional, cool house, cold house. So these are the 5 quantiles of the distribution of the entire Phanerozoic. So you can see the proportion of time that the Earth is spent in each state. Our current state, which is a cold house climate, is relatively unusual in the context of the last 500 million years of history. The planet has spent most of its time in a warmer climate state, certainly a warmer climate state than today. And we can look at features like, what does the pole to equator temperature gradient look like? So this is average air temperature across by latitude. And you can see that the changes, as may be expected, between the states are much bigger in the higher latitudes as we grow and melt ice sheets and things like that, and much smaller in the tropics, but that we do have more of a dynamic range in the tropics than maybe we would have thought, from around 20 to 35 C. And the other cool thing is that when we do compare our reconstruction to an independent reconstruction of carbon dioxide over these long time scales, we do find a relationship. Obviously, there's a lot of scatter in this one. And this is broken down by era. And the Mesozoic is kind of a mess, which there's reasons for that. But the Cenozoic and the Paleozoic, which sort of span the full range of cold house to hot house climates, do show a very consistent relationship between global mean surface temperature and CO2 is plotted on a log scale. Because CO2 forcing has an impact on temperature in log space, log 2 space. So the sort of log doubling scale that we mentioned climate sensitivity before, the slope of this line is around 8. And what's interesting to us is not only that it exists, I mean, maybe this is expected because CO2 should be the driver of Earth's climate, even on these long geological timescales, and that's not too surprising. But the fact that there's sort of the same regression line through the Paleozoic and the Cenozoic, this is the last 66 million years. This is the oldest era in our reconstruction from the Ordovician up to the Permian. And yet they show the same sensitivity of temperature to CO2, and they also fall on top of each other, more or less. Which, if you study deep Earth's climate, you might be scratching your head only because over the same time period, the sun's output has actually changed. The sun has actually gotten stronger over the last 500 million years. Solar luminosity has gone up. So we had long thought that carbon dioxide levels had to be higher in the Paleozoic systematically to compensate for that. And yet we don't find that that's the case. So that's one of the interesting puzzles that comes up from this long-term climate reconstruction that we're now sort of discussing and thinking about possible solutions. This is just CO2 and temperature. Maybe there's a methane story in there that we need to look at or something else. But nonetheless, you can see that CO2 really is the dominant control on Earth's climate, even on these long time scales. And look how tight the Cenozoic is. I mean, it's just, and this is when we have, of course, the best data for temperature and for CO2. So, all right. So just to summarize, we think that this method has been really effective at leveraging these two kinds of information, right? Climate models, spatially complete, physically consistent, but not real. They're a simulation. Data, real, they were there, they felt it, somebody felt it, but unfortunately not evenly distributed in space and time and uncertain. So by taking them both together, we can get a hybrid view of past climates that is spatially complete. But of course, the caveat, the method's not perfect. So for example, in the offline method that we're using, the patterns of change come largely from the climate models. There's a little bit of innovation from the data, but a lot of the pattern structure comes from the model. Now, we'd rather have a little bit more flexibility in that. So one thing we're looking into is actually doing true online data simulation. So actively running the model with paleoclimate data introduced. So that's one of the next steps. All right, so with that, I'm happy to take any questions. Thanks.
All right, so I'll manage the questions.
So maybe the graduate student could go and ask first. If the graduate student can ask first.
Sure, graduate students first. You're why we're here.
Could you explain how you got rid of high climate sensitivity scenarios?
Well, can you be more specific?
On the slide that with a 5-degree warming at the end of the century, if you were able to rule that out.
Yeah, so I guess it was to say that our estimate of climate sensitivity from the last glacial maximum, like the span of that probability, like doesn't even, like does not span to 5C at all. Kind of not even, you know, so basically we could say the paleoclimate doesn't suggest that that climate sensitivity is realistic. And so the LGM is one of those pieces of evidence. It's not the only one that goes into the IPCC assessment. So they use the paleoclimate, our LGM estimate. They also use estimates of like the Pliocene that I just showed you, not particularly our study, but a different one. Also, incidentally, rules out like 5 over 5. So there's multiple lines of evidence that kind of rule that out, but the LGM was definitely a player in that calculation, just to say. So.
I have a second question here.
Yeah, so in our discussion over lunch, you mentioned sedimentation in the geochemistry is one of your major signals used for paleoclimate reconstruction. So going back really far into the past, I'm wondering, are there like systematic, I guess, gaps in knowledge in terms of only certain environmental conditions favor preserving climate record? So are there holes, for example, areas that are particularly cold or dry, that happened before we have glacier records? So are there records of climate that we currently don't have a good understanding of because of the processes that are used to preserve the climate records in the first place?
Yeah, I mean, there's always biases in where the data can come from. And so in deep geological time, what happens is, it's especially kind of difficult is where you actually preserve sediments in these sort of long time scales. You can analyze for temperature proxies, you know, in the Paleozoic would be continental margin seaways, so marginal seas. So seaways, seas that are close to shore. I mean, that's kind of true today, even that's where most of our data come from, is like close to shore rather than out in the open ocean. But that bias gets a little bit, it gets worse as you go back in time. And so you do need these sort of like high sedimentation rate, like carbonate preserving areas to get those sort of special outcrops where people then can find it. So yeah, we don't have, the farther back in time you go, the more poorly sampled the record is, and you aren't sampling, you know, all kinds of climates anymore because, yeah, you simply just can't preserve the record. So that's always going to be an issue.
Yeah, thank you so much for the talk. So I have a couple of questions. So like my first question would be like, for the climate sensitivity, we're like saying like what is the increase in temperature, sea surface temperature by doubling of carbon dioxide. So can you please explain why it is that we define climate sensitivity this way, and why how does paleoclimate?
So can you rephrase your question? I'm not sure what you're asking.
Why do we define the climate sensitivity
That way?
Yeah.
Okay.
Doubling of carbon dioxide.
The reason that it's defined that way is that that's a really easy way to measure it in a climate model. So you can, in your climate model, you can just like double CO2 and then run it out and see what happens to temperature. And then you wait until until the energy balance kind of stabilizes. And then you just say, oh yeah, that's the amount of warming I get when I double. And so it comes from climate modeling. And that's how they sort of fundamentally measure how sensitive the model is to CO2. So, but I mean, it's still kind of a convenient way to think about it. You know, it just sort of makes a unit. Okay, the unit is doubling. You know, what's the response? And the temperature response, planetary temperature response, should be, you know, response to CO2 in a logarithmic way, anyways. So the doubling actually works okay. But I didn't invent that. You know, that's been around for a very long time. That metric.
Thank you. Yeah. I have one more question.
Uh-huh.
So in one slide when you showed this Eocene that time zone, so there was like warming near the poles.
Mm-hmm.
Yeah, it's like very counterintuitive for me. So could you say some kind of
Just like why that's the case?
Yeah,
Or
like
yeah.
so much warming in the poles?
Yeah, so that's a feature we call polar amplification. And so what happens is in pretty much in any time you warm the climate, even though you're warming the whole planet, like right now, you have a set of feedbacks that make the high latitudes warm more. And so one easy feedback to understand is melting ice, right? So in the high latitudes, especially the Arctic, there's a lot of sea ice, so pancake ice, it's floating on the ocean. As you warm the planet, the sea ice melts away. And now as it's melting away, right, at first it was bright and white and reflecting a lot of sunlight, so keeping the Arctic nice and cold. When you melt it, you expose dark ocean, and now it can absorb more heat. So you have accelerated warming, so you have this positive feedback from melting ice. And there are other feedbacks too involving clouds, but the ice one is a big one. And so a lot of that warming in the Pliocene is because we have removed a lot of the sea ice. And also in that case, the Greenland ice sheet is melted away and the Western Antarctic is melted away. So, yeah.
Thank you.
So I have a question for the data assimilation technique. So you mentioned that to do that, we should know quantify both the uncertainty of model and uncertainty of proxy data. But my question is, because we have a lot of different kinds of proxy data, how do you quantify, quantify the uncertainty of different types of proxy?
Yeah, that's a great question. So in these examples I showed today, we're working with proxies for sea surface temperature only. So we have, basically we have these geochemistry measurements we're making in the lab that are related to sea surface temperature, right? So we need to relate those things statistically. So what we do to do that is we have what we call these sort of calibration models. And most of them are based on measuring modern marine sediment, like, you know, that dates to today or pre-industrial at least. And then we measure that proxy in this modern sediment, and then we compare it to sea surface temperature that we've measured today, right? And so we can do that all over the planet and have this kind of calibration where we sample, you know, the whole range of SST today compared to the measurement we make in the lab, which is like an isotope measurement. And then we have a regression model, right, that's related to that. So the uncertainty of that regression model is one metric of proxy uncertainty that we can use for R in the Kalman game that comes from that global regression. But it is actually, yeah, you need to determine that uncertainty, as you pointed out, offline, like in another experiment, like with a regression model, or if you want to do it in a different way, you know, you can do that too, but you have to figure that out separately and then know what it is to put it in there. Yeah.
Well, we had one more grad student back here. Cal, did you put your hand up?
Yeah.
Are you a grad student? No. Oh, we're not. I'll store it. Please be gentlemen.
Well, thanks for the great conference. My question is very similar to the previous one. So first question is, how many observations did you use for assimilating each result? And also, I assume that the uncertainty of the observation data should be varied in time, like past versus far.
Yes.
And
Yes.
also, are there any variability in patient? Not very much. How do you deal with all the?
Yeah, so all great questions. So, okay, so when we assimilate, right, sometimes we have multiple observations per grid cell, sometimes we have 0, right? So, because this is the distribution, right? So if you think about, I mean, this is just an example, but let's say this is the data distribution, right? Then we may have grid cells where we have multiple observations that we can assimilate, and we have big grid cells out in the Pacific where we have no observation. So that grid cell doesn't get anything, right? So we only update where we can. If we have multiple observations in a grid cell, if they are separate, different kinds of geochemistry, we assimilate them both. If they are the same, then we take the average first so that we don't upweight a certain type of measurement. Okay, so, and then the second question was, the uncertainty, does it change through time?
Yeah.
So for this, yes. So for this time scale, we did change it. Following your logic that we should know that relationship better today and probably less so back in the deep time. And so we inflated the variance, the R variance, as we go back deeper. How do we do it? We experimented a lot with different assumptions about that to test that assumption. But it is kind of tricky because we don't know what it was, right? So we know it should have been bigger. And so we do, and we know also that certain geochemical systems have more uncertainty than others. And so that's also included in the time varying variance for here. For the other indicators, we do experiments where we essentially leave one out or leave groups out of proxies for internal validation to check the impact of different uncertainty choices on the internal validation. You know, this one we can't do much internal or external validation on. On the other studies I told you, we do that. And what was your other question? Okay. All right.
I thought really interesting, helpful. I have a lot of questions. One is, I'm wondering what the Like, what are the major sources of uncertainty in the GCM carbon sensitivities or climate sensitivities to carbon, and do your proxy syntheses like while they help sort of narrow that uncertainty, do they help point towards maybe what processes can be improved in GCM?
Yes, they do. So it's widely recognized that one of the reasons that this latest generation of or system models has higher sensitivity overall is because of changes in how they parameterize cloud and convection. So in these models, their atmosphere is usually something like 1 degree by 1 degree, and they are not actually simulating clouds. So they're not cloud resolving, so they're parameterized. Basically, they're a bunch of equations. The decisions that you have to make to do that, there's lots of different ways you can go. In this last round of model development, people made some similar decisions on how to change those parameters. And they all tune their models against historical, right? So all this to say is a lot of the high sensitivity came from these changes in cloud and convection parameter schemes that were made, right? But it's crazy because you can fit the historical time period with a low sensitivity model, and you can fit it with a high sensitivity model, fine, right? But then you take those two models out of that sample and they just completely diverge, right? So, which is exactly why Paleoclimate is great, because we can help with that. But we have a project right now where we're using this technique to constrain cloud and convective choices. So specifically trying to take it to model development. So the idea is like, if you train a model, they train them on satellite observations, like how well can I match satellite obs of clouds or something? And these are my parameter choices. And it's all done with like machine learning and stuff now as well. But you could get like 100 different combination sets that are fine, right? But then we can take all those combinations and we can run them for the LGM, and they are not fine, So knowing that, right, our idea is to do that, to deliberately perturb the cloud parameters in paleoclimate simulations with parameter sets that all would do fine today, and then use the proxy selection across multiple climate states to see if we can find parameter decisions that are more robust to large climate change. So that is a way to bring it back to model development already. So yeah, that's kind of the next big step.
Let's open it up to everyone. And, so for your future prediction, I understand you're going to go a lot to the past, but one of the things that wasn't in the past, looking at the prior record, is urban areas.
Right.
And so with the IPCC report coming out, are you taking that into account? Because I know we've got increasing greenhouse gases because of what we do in urban areas, but the urban areas themselves, it's a land use change, it's a land cover change that has an effect.
Yeah.
So does that play into your future predictions at all, or looking at that change from we got vegetation and now all of a sudden we have all these materials that's absorbing, like we were saying with the feedback loop.
So, I mean, the IPCC scenarios, they do take into account urbanization and stuff like that. So the socioeconomic, the SSPs, I can't even remember. Shared, thank you, shared. The SSPs, they all have, scenarios that do make assumptions about cities and where people are and land use and stuff like that in the future. So we don't include human impacts in the deep past that I'm talking about.
Right.
But I guess what would be relevant is the effect of the land surface on Earth's energy. And that is actually kind of a dark horse issue, I would say, in paleoclimate. Like, I mean, there aren't people, but we have these huge changes where, there was a desert and now there's a forest and like there's grasses and that can massively change the energy balance regionally, if not on a planetary level. And the problem is that we, in relatively shallow time, we have some indicators of vegetation change, like pollen records, and then fewer and fewer going back into deeper geological time. And so we do have these time periods where we're a bit, like, what would the impact be if this area was this biome versus this one? And it's a little scary, actually, if you play with that in a climate model and run simulations, you find that the impact can be very, very large. So I would say a next goal for paleoclimate would be to do more land surface reconstruction, because that's something that, even though we're talking about, natural changes in land surface, it's still relevant, because we still have questions about like how carbon sinks and sources are changing in the land. The land carbon sink is always like, depending on how you calculate it, positive or negative. So like these things are quite relevant actually for today. Yeah, so good question.
Any others? We have about 5 or 8 minutes left. Oh, not one. No prejudice.
The IPCC projections show the polar amplification, but they also show a tropical amplification with elevation.
Yeah.
And that has tremendous implications for glaciers and water resources for millions of people. And I wonder why that doesn't, are the models just capturing the lower surface and not the upper atmosphere?
Yes, I mean, well, our data assimilation products are mostly focused on, these are all SST, but I was just gonna bring it, well, whatever. Our data assimilation, like we only are putting in surface air temperature into the assimilation, so that's what we're getting out. So we do see a little bit of that, elevation amplification in major mountain ranges, for example, and I don't have it here, but in the Pliocene, our surface air temperature maps do show that. But we have not assimilated like upper, level temperature, for example. We absolutely could add that in, if that was of interest. And the other thing, of course, as you know, though, is with these models that we're using have very coarse atmosphere land. And so the Andes are like, it's like a cube. So they're not particularly great for mountainous areas, but we are doing simulations, paleoclimate simulations right now with a 25-kilometer atmosphere model and land, and we're experimenting with that for the Pliocene and some other time periods, and those are going to be really cool because they will actually have there's many places in the tropics that have that complex topography that isn't really represented in paleoclimate simulations right now, but will be much better in the 25-kilometer that we're now able to run on the new supercomputer. So that's pretty exciting. And I'm excited to see where that is going. So
We had a question over here. I think it was Lou.
I think it's really interesting, all these things. First, backwards, the CO2 sensitivity.
oh yeah.
What are the sensitivity of those models without your data? I'm just curious.
Oh, sorry, not this one, right? Or this one?
Yeah. Like this.
Oh, well, you might notice that this is had CM3L is the prior here.
Yeah.
Its sensitivity is quite low. It's like, I actually don't know if it's around 3, maybe even lower than 3.
Yeah.
It's very, very not sensitive. And you can kind of see that actually one of the problems with this model prior is that it never really gets very hot. You can see it just never really gets above 25, but we reconstruct temperatures that are higher than that in the data. So it's actually a very, very unsensitive model. But we should say that this number of 8 is not really, it is the temperature response to doubling of CO2 because this is a log 2 scale, but it's not an equilibrium climate sensitivity because this is like everything in the kitchen sink in there. So it's in other words, long-term Earth system feedbacks, right? So ice sheets are growing and decaying and continents are changing. Exactly. We're not breaking out that effect. So it's kind of like, we actually argued about the name for that.
Yeah, but I think
But yeah.
model, you can also, just without data, because you have all the change,
Yeah.
you can still plot the same way.
Yeah,
So
and it's not the same number.
how much is the difference? It's still low.
Well, you can kind of figure it out, just estimating, right, that model only has a range between 15 and 22. So you can imagine that the CO2 would be the same, but it would go like here.
Okay.
So it would be
So
a
it's
very,
still-
very shallower
still
slope. Yeah, it would be very, very low. So this is really coming from the data, and I guess you can see the Cenozoic, you know, in particular, are very tight. And we're not the first to show that. James Ray's group had a similar plot of this in a 2021 paper, with that number 8, which we're currently calling apparent climate sensitivity, which I think is kind of I don't know, it's kind of not a very interesting name, but I wanted to call it the Gaia sensitivity, and then people got super mad at me because there's a lot of historical baggage, as you might imagine. So anyway, it's a cool number. We're really mystified actually about that number, regardless of what you call it and why it is what it is. I'd never expected to get the same thing for deep time, let alone have them overlap. So that is a pretty spooky, I would say spooky result. That deserves some explanation. So
Then with the early cloud thing.
Yeah.
What do you think? I mean, this Christina showed this a long time ago.
Yeah,
No one
yeah.
does it similarly. But you analyze your data only so small. So what's the difference? Why their
Yeah.
data are so different from yours?
actually it's really simple. Yeah.
Well,
This is based on magnesium calcium of forams,
Okay.
and they basically they did not account for the change in the magnesium calcium of seawater.
Oh.
And it turns out the whole ocean MagCal has changed.
Mhm.
And in fact, a paper came out this year showing that it's probably even changed even more than I've assumed
Uh-huh.
in this. And that alone brings these dots way up.
Wow.
And this is the Alkanon data, which aren't affected by
But I saw that their paper had one airplane.
the Eastern Pacific.
the
Yeah,
Eastern Pacific
yeah,
one.
yeah. Eastern Pacific, I think, is more or less solid because the Alkanones and MagCal agree. I mean, the MagCal should predict a slightly
But
steeper.
the Eastern Pacific still shows, even if she used Elkanon, she will still show a.
Yeah, but there is no,
Oh,
not if you look at the Alkanones in the Western Pacific. So
Oh,
yeah, so they have Alkanones and MagCal,
Right.
and it's the way they plotted this is a little tricky if you actually compare them. They're not, but if you the real key record here is the red one, right? Which is basically
Yeah.
showing that the worm pool
Right.
isn't warmer. In fact, it's colder. So there's not too much argument that the Eastern Pacific warmed up by a lot,
uh-huh.
but the argument is the Western Pacific, how could it not warm at
That's
all?
right.
In fact, they predicted a 1 degree cooling of the Western Pacific
Yeah.
with this data.
Right.
And that's where,
I see.
if you reanalyze,
Western Pacific, Elkanon, Western.
there is some, but the problem is it's so hot that the
Oh.
Alkanone proxy tops out at around 30 C. But even with that, that's what this was. This reanalysis that we did using only Alkanones in the
Yeah,
west
yeah.
and Alkanones in the east. And you get -1, not
I
-3.
see.
But if you correct these data for the seawater,
Mhm.
they agree with the Alkanone.
I see.
So they were just wrong.
Yeah. Well, in moderate, and since who's not afraid, you completely don't understand. How can it be possible, right?
As long as the winds blow,
Yeah, it's.
you can't get to zero, right? I
anyway.
mean, you just can't.
It's better to wake up all these clouds. It's just, of course, if you change all the different clouds in different places, of course.
Right,
You can't.
Right.
do that. So,
yeah.
Well,
No.
we have just a few minutes more.
Okay, I'm.
I feel your pain.
I know we're kind of running over it too, but we're not really because.
Yeah, I think it's okay.
Yeah.
There's a few more, yeah.
We had another one over here, yeah.
Yeah.
So,
So you talked about it a little bit, how you go from climate to your proxy, and you use regression. And I assume it's a pretty straightforward connection with proxy with temperature, but most of the proxies are complex.
Yes,
And so there's so-called proxy system models.
yes, yes.
And like, to give an example, you can either compare your free range to temperature, or you can grow a tree.
Yes, yes,
And
yeah.
under that free range. So,
yes.
question is, well, the complexity does not necessarily mean improvement. So,
Right.
In your opinion, what is sort of the more important to go to higher resolution or to have laser? How far they increase the demand for computational demand sort of?
The proxy system modeling is really important, and yeah, we are using, you could call them proxy system models here. I mean, they're mostly regressions, right? But what they lack, and a formal proxy system model, like a real complete one, is talking about both about the geochemistry, but also the archive itself and how that might affect the signal. So there's several layers in a PSM. And in this case, we have the geochemical regressions, but we aren't doing anything about like bioturbation in the sediments or anything like that. So but we are using this method is totally designed for PSMs, and actually we have them integrated. And I should say that the software to do this is publicly available on GitHub in a really, really nice package put together by my former PhD student. And the paper accompanying it just came out in Geoscientific Model, and it even has a tutorial. And the only possibly bad thing about it is that it's written in MATLAB. And oh, the MATLAB users in the room are, so, you know, this is like, kids get off my lawn a little bit, but I'm old enough that when I was in grad school, you know, Python was not a thing, right? It was trashy. So we all use MATLAB, and now that there's fancy Python 3 and all this fancy stuff, okay. But it wasn't like that actually, even when we started working on this. So but it is a beautiful MATLAB package, and it's so fast because MATLAB is so good at linear algebra. Enjoy, but you can actually has PSMs in it. It has the Turing PSM, it has a Coral PSM, it has Sylvia D's whole Prism PSM package that's linked into it. So we're already doing it. You can make those as complex as you want. You're right, more complex does not mean better. And at some point, you can over parameterize those, right? So you should be careful, right, to only build PSMs that you feel like trust. But for example, we were just talking about magnesium, calcium, the SST proxy, it's actually multivariate. So it MagCal and 4-amps, the theory is that the warmer the water is, there's more magnesium in the calcium carbonate of the 4-amp shell, this little protist thing that lives in the ocean. And that's known that happens, but there's more magnesium in the shell when it's saltier. And the primary magnesium calcium of the seawater, just like the O18 of seawater, is also a factor because that is incorporated into the shell. And it gets worse. The magnesium calcium incorporation is also sensitive to pH of the ocean. And it's also very sensitive to preservation. So once that 4M shell falls, especially if it goes below the CCD in the ocean, it starts to dissolve, and then we lose magnesium. And so we also have to correct for that. So that forward model is actually, we have all that. It's all in there. And it's pretty complex. But those are all based on like lab experiments. So we know some of those sensitivities. I can code them. And that's okay. But yeah, so that's a nice thing about working in the forward space is it's okay if a proxy reflects, is influenced by multiple things. We can take care of that. If you work the other way around, right, you just have to make an assumption that something hasn't changed when you know it has. So that's the beauty of the method, is that whole comparison, that innovation is taking place in proxy space. So you don't have to assume that the proxy signature is just temperature, because you're just in the proxy space the whole time. So
thank you. Let's thank Jessica once more. It's been advised that the food is out, so have at it. And you